How does wave propagation behave in millimeter wave communications? This is what I will demonstrate in this video. We will utilize this setup here with the millimeter wave transmitter using 16 antenna elements and a single antenna at the receiver side. Right now they are 30 centimeters apart. We will look at what happens when we are varying the distance and when we are taking different objects like wood or metal foil and put it in between the transmitter and the receiver. How does that change the wave propagation behavior? If you want to know more about this experimental setup and millimeter wave transmitter, you should watch the first video in this series. The 16 transmit antennas are sending the same signal at the same time, and that is creating a constructive superposition. The signals are adding up to form a directivity towards the receiver over there. But apart from that, the signal energy is still spreading out. You can view it as having a balloon that you're blowing up and the energy is at the surface area. Well, the larger the balloon is, the weaker each portion of the surface area will be, and therefore there is less energy at the same time. In a basic scenario where you have free space line of sight, meaning that the transmitter and the receiver see each other and there are no object around us, we can expect the received power to reduce with the distance to the power of 2, because the surface area of a sphere with a certain radius is proportional to that radius squared as well. And I will now have a look at that we see similar behaviors here. In this graphical interface, you can see the received signal power in dBm, decibel of milliwatt. And this is a negative number because we are receiving much less than a milliwatt. Right now, it is minus 15 to minus 16 dBm. And the propagation distance here is 30 centimeters. The way for us to characterize how quickly the received signal power is disappearing with distance is to measure the received signal power as a number of different distances, and then we will plot a curve of it. We will measure the received signal power every 10 centimeters. So we start at 30, and now I will increase it to 40 centimeters. That's over here. The new received signal power is roughly minus 19.5 dBm. So we have an even smaller number. And you could see also in the graph here that when I was messing with the setup, the signal were going up and down because it interacts with my hands as well. Next, I will increase the distance to 50 centimeters. That's this. And we can see that now the signal power have reduced with another dB to minus 20.5 dBm. When we continue like that, we increase the propagation distance to 60 centimeters, twice the number that we had from the beginning. And now the received signal power have reduced with another roughly 1 dB to minus 21.5 dBm. This graph shows the 4 measurements, which are these black circles at 30, 40, 50, and 60 centimeters. And it is the received signal power that is represented on the vertical axis. And we have drawn straight lines in between these 4 measurement points. We can see that when the distance is increasing, the received signal power is decreasing as we would expect. There is a common way of modeling how the received signal power decays with distance, and it's based on finding a function where we have a constant divided with the propagation distance to a particular exponent. And the red curve is representing the best curve fit of that kind. The actual function that we got in this case was to take 18.7 and divide with the distance in centimeters to the exponent 1.95. And what this is telling us is that the received signal power decays roughly as 1 over the distance to the power of 2, which is what you would expect to happen in a free space line of sight scenario. However, none of the 4 measurement points are actually on this red line, which is telling us that a simple function like this is only providing us with the general trends and not the exact propagation behaviors in a complex environment with objects around the transmitter and the receiver, which is giving us these variations. I continued the experiment by moving the experimental setup to a hallway where I could measure the received signal power at distances from 2.5 meters down to 30 centimeters. This graph shows the received signal power measurement that I made from 30 centimeters all the way up to 250 centimeters, which is 2.5 meters. And I have once again fitted a red curve to capture the general trend of the measurements. In this case, the function that I fitted looks like this: 56 divided by the distance in centimeters to the power 2.17. So once again, the so-called pathless exponent was close to 2, which is what you would expect in a line-of-sight-like environment. But we also see how the measurements were bouncing up and down here. So sometimes the measurements were above what this model is providing us with, and sometimes they were below. And we can see that it has a somehow random-like shape, which is, of course, in reality, depending on what objects that were around. But in many propagation models where we are seeing that this kind of simple model is not enough to capture real environments, there's often a random term that is multiplied with this kind of model in order to generate curves that looks more like the black one here. So the general conclusion is that in both the short and the longer measurements, we saw that the received signal power decays roughly as 1 over the distance to the power of 2. But there will be fluctuations around that kind of model in practice. We will now determine how much different objects are blocking the signals in the millimeter wave bands. And we are particularly looking at the 26.5 gigahertz frequency. So right now, the transmitter is off. The receiver is still receiving, it says, minus 36.88 dBm. What does that mean? Well, it means that there's actually some noise in the receiver, so this is as low as it can get. And we need to remember this number because if an object is blocking us all the way down to this number, we can't detect it anymore because the signal is below the noise floor. So I am now turning on all of the channels here, all of the columns with transmit antennas. We now have a received signal power of minus 19.88 dBm, roughly speaking. So when the incoming signal is reaching this blocking object, well, we can measure the strength of the outgoing signal, and we can detect penetration losses down to 17 dB. So when we reach that number, we are down at the noise floor and we can't tell if the penetration loss was larger than 17 decibels or was exactly that number. So let us consider a few different objects. I start with wood. I put it in between the transmitter and the receiver. So we noticed that we were dropping from minus 99.88 to minus 21.22. So like 1.5 dB is what this one is blocking. Not very much. An iPhone. How much is this blocking? We have minus 35. See that it is almost down at the noise floor here, but not all the way. And it's going up and down. But we are still losing 16 decibels or something like that with a phone here. So millimeter wave signals are not actually going very well through a phone. Next object, some plastics. Put it in between, and we can barely see any difference. So this plastic here is almost transparent to not only our eyes, but also to these wireless signals. Metal foil, same thickness roughly, and I put it in between the transmitter and the receiver, and we can see that we are down at minus 36.88 dBm. So that was the noise floor. So metal is obviously not letting millimeter wave signal through. A shirt. 2-3 decibels is what this shirt is blocking. So half of the signal power is not going directly through your clothes. Next, we consider my textbook, Foundations of User-Centric Self-Free Massive MIMO. I put one of them in between here, and we lose something between 3 and 4 decibels. Another one. So twice that. Something between 7 and 8. And then one more. And now we are down to something like 10, 11, 12 dB that we have been losing. So the principle here is that every book is blocking something between 3 and 4 dB, and we add them up in dB scale when we have multiple of them, because all of them are blocking objects here. Here's an empty glass. I put it in between here, and we are going from -20 to -25 roughly, so say a 5 dB loss. I have a water glass, and now we are losing more like 11, 12 dB. So the water itself is blocking the signal in addition to what happens just with the glass. And finally, what about my hand? What happens if I am blocking the signal with my hand? And if you see, we are down at -36.88 dBm, which means that nothing of the transmitted signal seems to go through to the receiver. Here's a summary of the measured penetration losses. So plastic foil, almost 0 dB, wood, 1 dB, a shirt, 2.5 dB, one book, 3.3 dB, and 3 such books, that is 3 times that, so 10 dB, an empty glass, 5 dB, a filled glass with water, 12 dB, an iPhone, 15 dB, and finally for the hand and the metal foil, the penetration losses was above 17 dB, which brought us all the way down to the noise floor. In this video, we first had a look at what happens when we are increasing the distance from the transmitter to the receiver. And as we were expecting, the received signal power is reducing. After that, we had a look at how much different materials are blocking millimeter wave signals. And when the signal is not going through the object, it's either reflected or absorbed by the object. And we saw that plastic, papers are letting the signals through very well. If you have a thick book, still only a few dB are the blockage. While objects like metal foil or even your hand is blocking almost all of the signal. In the next video, we will have a look at the phenomena of constructive and destructive interference.